Okay, so we were just starting to talk about the rotation curve in the last video, and so what this dotted line here indicates what the velocity of the stars in the outer part. So this axis, the horizontal axis here, is distance from the center. So remember, we're about 8 kiloparsecs. So this, this is getting really far from the center of the galaxy, and so the stars should, their speed should drop off, just like, for example, the planets going around the sun, right? Neptune is moving a lot slower than is Mercury, right? Mercury is moving the fastest because it's closest to the sun. So the closer you are to the center of mass of the galaxy, the faster these things should be going. Anyhow, this is exactly what should happen, but that's not what's observed. What's observed is that it's almost horizontal, like the speed of the galaxy, the speed of stars in the galaxy further than 20 kiloparsecs away are moving at about 225 to 250 kilometers per second, and they go up slightly. So they start to approach 250, or even a little bit more than 250, as you get further and further out, which doesn't make sense at all. Okay, so this is what Vera Rubin originally discovered with the Milky Way. And since then, by the way, we've seen this same rotation curve with all spiral galaxies. All right. So what is this? There's got to be something. There must be some kind of gravitational force way out there in the halo, right? So this, 35 kiloparsecs from the center of the galaxy. Now you're talking in the realm of the globular clusters. So you're well into the halo of the galaxy, and so we can't account for this this kind of speed with just the globular clusters, right? We see about 150 of them. There might be a few more, maybe a dozen or so. Who knows? But even that, though, would never account for this kind of slight rise in the velocity of those outer stars. They should be moving slower, definitely not faster. So, of course, astronomers since the 1970s have actually come up with a name for this stuff. The material that we find in the halo of the galaxy has now an official name. It's called dark matter, and the reason it's called dark matter is not because of just visible light, but no form of light seems to interact with this stuff. We know it's there, right? This is the proof that there's something there gravitationally influencing the stars very, very far from the center of the galaxy. And so the only thing that can account for this would be some kind of matter that again, it has a name. It's called dark matter, but we really don't know what it is. So some people have proposed, what if it's just black holes that don't have an accretion disk, let's say, but they're just, we don't have any mechanism for creating that many black holes out there in the halo that just simply would be, by themselves. There's a possibility that there could be a few, certainly even a few hundred, but it's not going to account for this curve going up like this. In fact, there's a tremendous amount of matter out there in the halo, but we don't know what it is. It's called dark matter. All right, so some things that have been proposed are brown dwarfs. Remember, these are failed stars. If there's enough of them, maybe that could influence this rotation curve. Very faint white dwarfs, even red dwarfs. So those are the best things that are star-like objects. And then some people started thinking, and this was in the 1970s. They came up with these odd, strange subatomic particles that were predicted by some of the theories that deal with subatomic particles, subatomic physics. But we don't have any evidence for this stuff. And actually, here, let me see if they start talking about it. The two general categories are called machos and wimps. They're acronyms. Like wimps are like weakly interacting. I don't know. I forget exactly what the acronym stands for. And machos are like massive something halo objects. So. We'll see if it says this a little bit further on. But again, even if these are just proposed ideas, we really don't know. All right, so here is using the Hubble Space Telescope to look for these red dwarfs, and of course we found some of them in the halos within the globular clusters. But there's just not enough of them to account for the rotation curve, right? It's the fact that it's going up. One interesting thing, a tool that we can also use, from Einstein's theory of general relativity. Remember, when light passes close to a massive object, it bends. It'll change its direction due to the curvature of space and time near that thing. Near that object, and so that's what's called gravitational lensing. And so we actually have telescopes that will look for this. These are automated telescopes I think one of them is called the Sloan Survey, and so like night after night, these things are. It's actually more than one telescope. They're all around the world, and they're looking for these gravitational lenses. But thus far, the number of white dwarfs, we have found some white dwarfs, but it's still only, in the halo, I'm saying, it's maybe 20% of the whatever this dark matter is. So there's something there that we just don't know what it is. I mean, there's been lots of, this is part of the current research in 21st century astrophysics, is to figure out what the dark matter is. All right, so again, that's the first sign of that was within our galaxy. It's going to turn out that there's dark matter around every galaxy. In fact, just to let you know, this is to jump ahead to the next couple of chapters. We can actually map the dark matter, right? Using these gravitational lenses, or using gravitational microlensing, and even just regular old gravitational lensing due to the bending of galactic light. So you have some galaxies that are really, really far away, and as that light passes near another galaxy, it's bent. And that bending, Einstein's theory of general relativity predicts how much that bending is going to take place, and so we can actually measure that, and we can look and see, in different forms of electromagnetic radiation, exactly how much matter is there in that particular galaxy, and there always seems to be more matter. So it's both visible matter and dark matter that makes up these galaxies. All right, and there's always a lot more dark matter than there is visible matter. Now we're going to turn to the center of our galaxy. Remember, we cannot see the center of our galaxy in the visible part of the spectrum, so we've used other, of course, because there's gas and dust that basically blocks our view. The photons can't pass through, and so what we have done is looked in other parts of the electromagnetic spectrum. This is, for example, looking into the heart of the galaxy in the direction of Sagittarius. that's so that's a big, huge area of the sky. We're actually looking into a particular part of the constellation Sagittarius in the infrared region, with radio telescopes, and with the Chandra X-ray Observatory, which of course is in space. All right, so these are some different images of the center of our galaxy. So here's one feature of the center that I want everybody to remember: the stellar density, that is the space between stars in the near the core of our galaxy, is about 1 million times higher than out here where we are in the spiral arms of our galaxy. So there's 1 million times more stars packed together, in a given volume. All right. We also see a ring of molecular gas about 40 parsecs across, and very, very strong magnetic fields. There seems to be a rotating ring or disk just within a few parsecs, that's a few parsecs across, and there seems to be a very strong X-ray emitter right at the center. And the center, by the way, it's called Sagittarius A star. So that's the black hole at the center of our galaxy. And I'll talk about how we figured this out anyhow. And that was figured out in the 1990s. So this is called a supermassive black hole. The accretion disk, remember, this is just matter that is piling up, has not fallen into the black hole yet, but is accumulating in an orbit around the black hole. And as it orbits the black hole, this stuff rubs against itself and emits X-rays. All right. So in the 1990s, we using infrared telescopes. In particular, there was this picture right here, the one on the right hand side, is actual stars orbiting some object, and that object has been called Sagittarius A star. There's the symbol right there, Sagittarius A, with a little asterisk above it. That's this point right here. And so what we've done or what we did in the 1990s is using the Keck telescopes. There's these twin, very powerful telescopes in Hawaii on Mauna Kea, and we've basically watched these stars. Let's see, especially where's S2? Are they showing you S2? Oh, this one right here, S2. So this particular star, we've watched it go all the way around, and there's an object right here that's, according to the laws of physics, this thing has to be 4 million times more massive than our sun for these stars to be orbiting in the path that they're taking. And so that's the supermassive black hole at the center of our galaxy. There's also a huge outflow of gas from that seems to be coming from our galaxy. Basically, it's like if you what's a good example? If you had like a small drain, let's say, and you poured, you opened up like a fire hose, and you expected that fire, all the water from that fire hose to go straight down the drain. That's not going to happen. Some of that water is going to splash out, and in fact, that's exactly what we see. And these also follow along magnetic field lines. All right, let's see. Oh, and look at that. Looks like we are done. Okay. There seems to be, there's a mixture of old and young stars there in the galactic core. But the main thing about the center of our galaxy is there's this supermassive black hole. Again, it's 4 million times the mass of the sun. There are some that are billions of times the mass of the sun in other galaxies. And it seems every galaxy we see, and this is the subject of the next chapter, of course, but we're almost there. Every galaxy we see seems to have a supermassive black hole at its center. And in fact, it probably has to do with this, the creation of galaxies